Hey, hey everyone. So it's 6 o'clock now. So I think I'm gonna go ahead and get started in just a second here. With our third discussion of the semester. And this one's on stacks and cubes. So I'll go ahead and share my screen and then we can get started. Okay. So yeah, discussion 3. Stacks and cubes. Endless. That's right. So start the slideshow. So what we're going to go over today is we're going to start with the quiz review. Then we're going to go over a little bit about technical reviews, and queues, stacks, and then we're going to talk about lists a little bit with slow pointer, fast pointer. Okay. So to start, this isn't exactly your quiz, so I'll talk more about your quiz, but the next slide will not be on your quiz specifically. Let's see. Yeah, that's fine. So hopefully y'all can hear me, but looks like sound isn't very high. I don't know, but in any case, yeah. So we'll talk about the quiz. So this wasn't exactly your question, but I'll talk about your question more specifically. So you had, rather than this, I know you guys had like a list of words and you were looking for a peaky string, right? So it was the longest string, right? Or not the longest string, it was longer than all of its neighbors. So if it was like here, for example, it was longer than this guy. If it was this guy, it was longer than this one and this one. And if it was this one, then it would be longer than this, right? So in this case, right, what we needed to consider was the general case, right? The general case was anything in the middle of the array, right? So like anything like this element. But then the other thing that I think a lot of people had trouble with was the ends of the array. Yeah, the ends of the array, like the first element and the last element, comparing them to the previous one. Because if you just did it naively, you check every element compared to the last one, the previous one, and the next one, then you're going to go out of bounds, right? Like with this one, for example, this first element, if you're checking -1, there is no -1. If you're checking this one, you're doing +1, there is no +1. So you need to handle those slightly separately. That's one thing I noticed a lot of people kind of had a little bit of trouble with. But overall, I thought most of the answers I looked at were pretty good. So that was the main thing, I think. As the actual time complexity, it's important to kind of give an explanation for your answer. Like I noticed some people said like ON because you're going through every element, or ON times T because find the length of the string to T time, which is good. Like you should be saying both. Like either one of those is fine, right? But like it's important to just justify your answer. Right? Like if the length only takes one time, if that's an assumption you make, then that's fine. But you need to say it, right? You need to state your assumptions and like explain why. You got the answer you did. But overall, I thought a lot of names. Okay, so this was a solution just for this question in particular, but again, it's not your question. So we can kind of like skip over it if you want to look at it more. You're welcome to. And you guys had something similar to this as well. This is another question I noticed a lot of people had a little bit of trouble with, which is fine. But this one is a little different because asking for big omega, you guys have big O, I think, on your quiz. But either way, it's pretty similar. Because for big omega, right, that's saying that it's lower bounded by this, right? And for big O, it would be upper bounded by this. So if we say, okay, which of these answers is big omega of this, right? Then like we're basically looking for, okay, what is lower bounded than this? Or what has a larger growth rate than this? Well, n factorial this, right? Anything with n to the fourth, again, you can drop constant terms out front. So we get this. And surprisingly, this one as well, because like this one looks like it grows faster, but it really doesn't. And the reason why not is because we consider, as long as k is a constant, then log k of n, right? For any k is going to be the same as long as k is a constant. And the reason why is because if we consider what we have to do, right, log base 3 of n, log base 3 of n is really the same as like, yeah, it's log 3 over log 2, right? Something like this, right? We can use log rules basically, times log 2 of n. right, we can use change of base formula. I think might be on the next slide anyway, but using change of base formula, the only thing we have up front is a constant factor of logs. So for any k, right, they're all the same. So that's why this, in this example, even though this is supposed to be lower bounded, like these are the same, right, order. So that's why that would be an answer. If we're looking for big O, then this would also still be an answer, right? Because it's still upper bounds this, right? Like this one still is an upper bound because it's up the same order. But again, for big, if this were big, if we were looking for ones that are big O of this, right? We're looking for anything that's upper bounded by this. So this one is, this one is, this one is, this one is. Okay. So hopefully that makes some sense. Yeah. So like we were saying, right? We want to find all solutions to n. We want to see all ones, like for big omega, we want to see all ones that grow as fast or faster than that. So n factorial grows faster than polynomials, and for again dropping constant factors, n cubed, and yeah, essentially grow at the same speed. Because again, using log rules, they do grow at the same speed. They actually do. It's just a constant factor different. And again, we drop constant factors, but you can get between any two logs with change of base formula, and change of base just leaves you with a constant factor up front. And since we drop constant factors, that's why this is. Okay, so I don't know. I thought that was pretty cool when I learned that. So hopefully you guys remember it, I guess. Okay, again, these errors aren't like specific to your quiz, but you maybe will get something out of them. Yeah, so best case time complexity. Yeah. Sometimes, yeah, you assume, like I noticed, and this was true on this quiz as well, people assumed when n was 0, 1, they have the best case time complexity of 1. But that's not really how time complexity works, right? Because you still, like for best case, it's still dependent on the input, like size. But like again, just like we talked about last week, if there's some property of the input, like sortedness or whatever, that's different. But for just size, it's still like, depending on like n rather than 1. So you can't assume a small input size. You can talk about small, or you can talk about like sorted order or something like that, because that actually affects how if that affects how the program runs. Like size of input doesn't have anything to do with time complexity, really, because like a small input, it's still like O(n). For example, if it's one check for an input size 1, then you're still checking n. It's just n is 1. So just a reminder about that. So yeah, you always assume large input. Yeah, this wasn't really a problem on this one because, or too much of a problem, at least on the pseudo question, because it was okay if you assumed it was a 1. The length, find the length of a 1. But if you compare strings, for example, that takes O of t time or O of n time or whatever you call it. And this didn't really impact us too much for the actual programming question. And yeah, confusing these two is also bad because this one acts, remember, is like lower bound. This one, it's upper bound by this. So, yeah. Okay, so any questions about the quiz? Since I don't think you guys are here, if you have any questions about the quiz, feel free to send me a message on the Slack. I'll get back to you as soon as possible. Okay. Yeah, or just come to my office hours or Josh's office hours, or yeah, just if you have questions, ask them. Okay, so now we're going to talk quickly about technical interviews. So what is it like to be in a technical interview? Maybe some of you have been on them before, maybe you haven't, that's okay. So always do your research first. And I guess hopefully this should seem kind of obvious because like, you want to know about the company before you actually do an interview with them, because yeah, you want to have something to talk about. You want to like have a good understanding going into it, right? Yeah, and for example, like it really depends. Like if it's hardware, maybe the last like system, like hardware design, I don't know, or data structure algorithms, software, depends. But also it's good to right? And yeah, you might have multiple rounds, behavioral technicals, like questions like these, right? Where they ask you to actually like solve a problem, maybe. Behavioral is like seeing if you're a good fit. And so yeah, a lot of times you'll get a problem either orally or they'll write it out. I know a lot of the companies have like a shared document that you have with your interviewer, and they maybe ask you questions over the phone and they explain it, but then they share like a document with you and you're like writing on that document. So yeah, and it's also really good to ask clarifying questions because I know, for example, in my experience, there's one time where the question my interviewer was asking didn't make a lot of sense, and it actually was because the question was a little bit flawed. And so like as long as you're engaged and showing your engagement, that's a good thing because it shows that like you really know what's going on. But also, if there is something wrong with the question itself, or like if someone makes a mistake, I mean, we're all human, right? It's they may not be a solvable question. It's good to, and also it gives you some time to like walk through the edge cases, right? Talk about it and think while you're talking like, a little bit. It gives it a little more time to ask clarifying questions as well. So I recommend you all do that. Yeah. And then you start to describe your solution. And try and do that before you write, because like planning before you're writing, if you start writing stuff out, it'll take you a while maybe before you notice something's wrong. But if you talk it out, a lot of times you'll realize if you did something wrong earlier. That's good because they want to see like how you think. Yeah, so next slide, there's more comprehensive description. And then a lot of times at the end, so how it usually goes is either they'll ask you a question about yourself at the beginning. A lot of these companies do that. And then they're behavioral type questions, right? Like about you, like telling about yourself and stuff like that. And then it's technical interview question. And then at the end, there's time usually for you to ask questions like that. And then you want to know a little bit of the company, so you can ask like reasonable questions about what they do. Okay. Technical interview or technical question flowchart. So one, always listen. Make sure you pay a lot of attention because yeah, it's of course good to pay attention to what people are saying, and it can help you understand. Right? Start giving test cases. This can be good to help you kind of understand it better, and maybe visualize it in your head as well. Having a brute force solution isn't a bad thing, as long as you optimize it during the interview. See, like, but if you brute force it, right, maybe then you'll understand the question better. Right? So you can like, oh, okay, I brute forced it. Now I know what I'm doing. Right? And then maybe you can think, oh, data structures or anything like that, or an algorithm that help me. And then you optimize, right? Brute force, then understand, optimize, and then yeah. Bottlenecks, unnecessary work, and duplicated work. So duplicated work, you can try to get rid of, right? Unnecessary work, get rid of, and bottlenecks, get rid of them. And then you can walk through it with them and talk with them and then review it. And I think a big thing is as you're writing code, don't go quiet, like actually talk to your interviewer. And a lot of times they'll help you along the way as well. So definitely important to talk. Yeah, and then afterwards you implement it, right? And even while implementing, you need to talk, or it's best to talk. Then you test it. So test it by giving like simple test cases. Maybe they'll give you some sample test cases, and you can just think through, okay, will this work or not? And then coding review, 6th edition, page 62 is I guess where this comes from. But this is generally good advice. Just kind of go through this. Probably the most important is really understanding the question well. Talking always, because they want to see how you think. So how do you prepare for technical interviews? Yeah, so I think there would be some sort of panel of past interns talking about applying, interviewing, and working. But I think the best way is probably just find practice questions online for like interviews and things like that and try and do those. And also, of course, read up on the company report. And so stats. Yeah, okay, so now on to the actual lesson. So that was, I guess part of the lesson is about interviews and stuff. So I'll talk about stacks. So stacks are an abstract data type. So its implementation different, but its operations should be the same across all programs pretty much. And it follows first in, last out. You can kind of think of them as dishes, right? Last one to get on top, the first one removed. So I don't know. I was thinking, yeah, like you're pushing something down, right? Like then the thing you put on last is like the first thing off. So like it has a very like physical interpretation. Like you can like think of it like you think of things in real life, right? So like a lot of things in real life are like, I don't know, first and last out. Like I guess the example of dishes is a good one. Because with dishes, right? When you put dishes, let's say you have a cabinet, you open your cabinet, you put dishes there after you clean them. And well, which dish are you gonna grab? You're not gonna grab the one on the bottom. You're gonna grab the last one you put on. So that's kind of like how a stack works. The last thing you put on the stack is the first thing you take off the stack. So common stack operations. There are only a few that are you really need to know, which I guess is good. So pushing something on the stack is putting something on the top of the stack. So push, for example, here, 2, you push 2 onto the stack. It's like putting a plate on the stack of plates. Pop is when you take something off of the stack. So with a stack of plates, you take the top plate off, and that's it, right? Top or peak. So these are 2 different names for it. I think Java has like something else. Yeah, you have like hole or something. But anyway, but generally it's called top or peak, and in C++, I think it's top. But yeah, it's or peak. I think it's actually peak, but whatever. It's one of those. And yeah, so when you peak an element, right, you're looking at the top element. So that's like, okay, I want to know which plate is on the top of my stack. Like I have a stack of plates, right? Oh, my blue one is on top. And you can just look at the top, right? You look down at it. Okay, here's my stack. Perfect. You just see the top thing, right? And then if you want to take it, you pop it up, right? Empty or is empty. And it's just saying, okay, is it empty? And if it is, right? Like if I can look and I see the cabinet, right? If it's in the cabinet, right? I don't see any plates on it. I'm looking down, I don't see any plates. It's empty. Right? Now, this was just the formula. And stacks are really useful for like things like depth first search, which I guess we'll talk about later. But depth first search is generally like if you're searching, it's kind of like how you do a maze, right? You go until, we'll talk about this, I guess, in future weeks, but it's kind of like how you do a maze, where you go until you reach somewhere where you can't go any further, and then you go back to the last place you had to make a decision. Then you choose the other way, and you keep going. Eventually, you'll get there, right? Like if I'm going through a maze, oh, I reached a wall. Okay, where's the last time I had a branching decision? Okay, go the other way. Yeah, like that. A reversal algorithm as well, and function method cycle. So yeah, believe it or not, like the stack that is like the stack that you use when you write programs is a stack. So here, just like a stack. So yeah, so like things like recursive functions often make use of stacks because you're literally using the call stack. An expression evaluation as well, and backtrack, and also syntax parsing, and yeah. So there's just different applications for it. For queues, with queues are a little different, and these are also an abstract data types that exist in many programming languages. They might have different function names, but they're generally all do the same thing in different languages. They're different than stacks. Because remember, stacks are first in, last out, and queues are first in, first out. So what that means is it's like a queue, a regular queue, like any place you would see a queue, like you go to a restaurant, there's a queue of people. The first one in is the first one served generally, right? So like a buffet line, right? First person in line is the first to get food, right? There's no cutting. So queue has NQ. So that's something you put something in a queue, like it's like getting in line, right? GQ is when like you take the first person out of line. So maybe only a certain number of people because of COVID are allowed into the buffet station. So you're all waiting in the queue. And then when someone leaves, like the buffet, right, then they can DQ. They take the first person out of the queue. And then there's also front or peak, where you just look at the first element, and then is empty. See if it's empty. So queues are breadth first search, which are a little different from depth first search. And again, we'll talk about this in future weeks, but that's like where you check all of the neighbors of where you are now, and then keep going outward. So yeah. Scheduling algorithms and handling interruptions in real-time systems. And you can build system units. Okay. So a lot of this will go into more detail later, but or something. Yeah. Okay, so for time complexity, this is a tough one, I guess. So go ahead and pause, and you can unpause when you're done. Okay, so for all of you who answered them correctly, good job. We'll go ahead and do all three at once. So time complexity of push or NQ operation, stacks and queues. Well, if you think about it, we're just adding one element to the top or the front right? And or the back, right? We're just adding an element, right? And that's it. Like, so only O1 thing. It's time complexity of pop and GQ operation for stacks and queues. So you just take one element. That's it. It's also O1. And time complexity of top, front, peak for stacks and queues. Again, we're just looking at the element. So also O1 time. So how would we reverse the linked list? This is another question for you guys. So we can look, right? And so yeah, we return reverse help here in reverse list. So reverse helper, right? If our current put is none, right, we return the previous. Otherwise, we can do it recursively, right? We call reverse helper, and so we just for each element, we just go to the next one. Let's switch. So yeah, we can use a stack. It can be done recursively or iteratively. So like I was saying, all recursive. Yeah, okay. Like I was saying, recursive algorithms use a stack basically, right? Because they use the call stack. And then, yeah, it can be done recursively or iteratively. Yeah, you can do any recursive algorithm iteratively as well. So yeah, our primary function calls a helper function where previous no. It takes in previous and the current to reverse their connection, right? So now our base case is that, and a recursive is reversing the connection, right? And then we return the head. So that would be the recursive call and stuff. So basically, we're just, in order to reverse it, we have to reverse the connections, right? And then for the last element, we make that the head. And of course, here it's O(n) space and time complexity. And the interesting thing is it's clearly O(n) time complexity, right? Because we go through n elements, or we're going through every one, right? But it's also O(n) space. And the reason why it's O(n) space, even though it's recursive here, is because if you think about it, we actually have to, like each of these goes on the stack, right? The call stack. So we have to go through, and like n of them have to go on the call stack. So it's still O(n) space, even in that case, right? Yeah. So like that's O(n) extra space. Of course, like it's O(n) space also just because of the size of the list that we're using. But yeah, see, notice how we call reverse list 1, and then that's no 1, 1, 2. We swap them, 2, 3. We're swapping those. But notice how all of these are going on the stack. And so our stack has n things on it, or I guess n plus, yeah, I guess it's n plus 2. Yeah, n plus 2. Yep, so hits the base case, returns 5. And then our new head is 5, right? So we have 5. 5's next becomes 4. 4's next becomes 3. 3's next becomes 2, and 2's next becomes 1. And then we return it. And notice how like the call stack works just like a regular stack, because this is like we pushed all these things onto the stack, right? As we went. We called reverse list 1. We pushed reverse help. We pushed reverse help. We were pushing all these on there, right? And then as we went through, right, we finally hit the base case. And our base case was when current is none, right? Because null is current, right? So, right, null here is current here. So there's nothing left. So we hit the base case, so we just returned 5. And in this case, right, we're gonna now pop the stack. Or it's done for us because it's a recursive function, right? But it's the call stack. So yeah. Then what we do is 5's next. Notice we called this here, so now we finish the method, right? For all the previous ones. So we're gonna finish for reverse help for 5. So it changes 5 next to 4. 4's next becomes 3 based on this. 3's next 2, and so on. And then we return this. Okay, so hopefully that made some sense about how we did this. Okay, so with linked lists technique, we have something called slow pointer, fast pointer. And for this, yeah, basically what we have is we have 2 pointers to our linked list, and one goes faster than the other. And this allows us to go through the list with only one pass, which is pretty cool. Yeah, so you can solve a lot of linked list questions this way. Have 2 pointers to iterate through one linked list, one that's fast, one that's slow. Yeah, so for example, you can have the slow pointer move one node for every two that the fast pointer moves. And that way it will go twice as fast, the fast one, right? Like notice, the fast pointer will always be twice as far through the array, or through the linked list, as a slow one. So that's pretty cool. We can look two times as well. And yeah, if we don't know the length of the list, linked list, this can help us a lot, right? Maybe you can see how doing something like this, right, might help us find the middle element, maybe, if we don't know the length, right? So yeah, but okay, let's talk a little more. So let's just talk a very general case. So I remove the nth node on the end of a linked list, right? Then all right, I'll just draw this out really quickly. We have a linked list, right? Let's say we want to move the second to last. We're going to remove this one, right? We don't know how long it is. We could go all the way through, right? And find the length of the linked list. That could be our first pass. So that's an option, right? Option one is to go through all the elements, right? Find the length and then do length minus n, right? And go through the list again. And that's an option, right? That takes two passes through the list. So maybe we can try using what we just talked about, right? Slow pointer, fast pointer. Assuming that it always exists. So here, if we have n equals 2, right? Yeah, if we remove the second to last one, right, we have 1, 2, 3, 5. So we removed 4, second to last element, right? Okay, so maybe you can think a little, like, how could we improve, right? Because, yeah, slow pointer, fast pointer is not the only solution. And then, yeah, here, just like we talked about, one solution is doing two passes, like we just mentioned, and we count the number of nodes. And the second one, we do the n minus 1 node. It's still O in time, but it's two passes. So that would be like big O of 2n, which is still O(n), but maybe not as good as 2 pointers or fast pointers. A note is like, yeah, slow pointer and fast pointer. It's really, really helpful. It really is for linked list problems. But it doesn't always apply to linked list problems. So it's important to really think about, okay, when given a problem, does it apply here? Can I use it? Because it's good because you can do things in one path. It might take two otherwise, but it's not a silver bullet, right? So just always important to think, okay, can it help me here or not, right? So maybe try and think. I know the code is in the next slide, but maybe try and think about it before we look at it. Okay, now we can talk. So what we notice here is we know that it exists. So you don't have to check for null or edge cases or that, but you would otherwise, right? But we're already told that it's not a problem. Okay, so we have a method header, input and output. We have our count variable to keep track of how many nodes the fast pointer is ahead. And so that's count. We're basically trying to keep track of how far ahead the fast pointer is, right? And then we only move the slow pointer, the fast pointer moves n nodes ahead. And what that means, right, is we keep going, we move the fast pointer like n nodes ahead, right? So now it's n ahead of the slow pointer. So now if we have this node is slow, right? And then we have like dot, 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 whatever, right? And this one over here is our nth node. Now this is where our fast one points, right? Now we can keep moving both of them one by one, right? Until we get to the end. And if we move them one at a time each, then the distance between like these two will still be n, right? So even if I move this one and like this ends up being my, like this is my last node, and this is last minus n, for example, right? The distance between them is still n because I only moved the fast pointer to get to n, and then I move them each one at a time, right? So yeah, we only move the slow pointer, fast pointer moves n as the head. And then we catch the edge case where the head is the nth node. So you have to be careful about that as well. Yep. And we have to remove the nth node. And then we remove the node, right? So you remove it by having the one before it points to the one after it, right? And then just delete it. Okay. So yeah, let's go ahead and draw this out a little more, right? So let's see the edge case where there's only one and we want to remove the first to last one, so the last one, right? Okay, so fast is head, slow is head, count is 0. In this case, we're gonna have fast is null, slow is head, count is 1. Then we have n equals count, right? So we set head equals head next. Head is null, and return null, which is head, so perfect. So for our edge case, this works fine. Okay, what about the general case? Well, with n equals 3, 1, 2, 3, 4, 5, or 1, 2, 3, 4, right? What we want to delete is, yeah, well, we have 1, 2, 3, and 4 in our list. And it's 3 is the third from the end. So not the third node, but we're going to remove 2. So 1, 2, 3, counting from the end. So these kind of things are things that are good clarifying questions on an interview, for example. So, okay, let's go there. Fast is 1, slow is 1, count is 0. So actually, let's draw them. I think this might help. So if we draw it like this, right? At the beginning, fast is here, slow is here, right? And then fast moves up 1 because it's not at n yet, right? So fast. And we move this guy over, right? We moved fast over. And then we now count as 2, right? Because this is fast as a 2. And now fast becomes, whoops, yeah. Fast is, whoops, I think I forgot to move it a little more. That's my bad. Another time. Yeah, so now fast is here, right? And then count is 2. And now we have fast goes up to 4. And what we do now, not what now we do, that's such a good image. Okay, whatever. So now, right, we found the end, right? It's going to move to null, right? But because count is 3, slow doesn't move, right? So you exit the while loop, and fast is null. Slow is still the 1 node. So now what we do, right, is now we're going to have this guy point to this guy, right? And what that's going to effectively do is drop this one from the list. And so now we have 1, 2, 3, or 1, 3, and 4, and we drop 2. When count becomes 4, right? Yep, so in the else condition, we set slows next to the 2 node, from 2 node to the 3 node instead. So we skip the 2 node, right? So we basically delete it. So we have 1, 3, 4, and then we return the head. And we have to return the head because if we return, for example, return 3, then we're only gonna have 3 and 4, right? Because it's they only have next pointers, so it doesn't know about the ones before it. So that's why it's important to return head, which is 1. Okay. So given the head of linked list, we can write an algorithm that finds the middle of the linked list. So maybe, okay, so we'll talk about this. So maybe some clarifying questions you want to ask that's like on an interview. So you want to know, okay, is it a doubly linked list? Do you want to know if the head can be null? Are there any space or time restrictions, right? What if the linked list has an even number of nodes versus an odd number of nodes, right? Is it different? And it would be, right? Because the middle element, there is no middle for it's not even. So we might need to do something like get middle is node 2. And now maybe you can also start thinking about how we can kind of maybe expand upon this, right? Because here we're removing the nth node, right? But now we notice, okay, maybe we can use slow and fast pointers again. Because we want n over 2, right? N is the length over 2. So we don't know the length, but that's okay. Because it's a very similar idea, which is kind of nice, right? So again, we have our method header with input and output, our control variable to handle movement of the slow, whether we're going to move the slow or not. And the while loop, we want to move the fast pointer 2 nodes for every 1 node that slow moves, right? Because we want And that's the really big thing here, right? That's the key. Because what we're noticing is we want the middle node, right? So if the length is, I don't know, like really long, right? What we want to do is, okay, fast moves 2, slow moves 1. So, well, if we think about it, right? If we consider for a second that we haven't looked at the rest of the year, so we haven't looked at the rest of the list. We've only looked at this part of the list. From our point of view, this part of the list, slow is halfway through this part of the list, because fast is at the end of this part of the list, and slow moves 1 for every 2 the fast moves. So for this part of the list alone, slow is in the middle. But then, if we keep moving fast 2 and slow 1, what we're effectively doing, right, is saying, okay, now this is our end so far, right? And what we notice is that, okay, look, slow is still in the middle. So it's almost like with induction, if you've taken discrete, which you probably have. So like with induction, like you keep an invariant. It's something that's, an invariant is like something that's true, and it remains true so long as a condition. So it's really a lot like, you can think of this, you can probably, or you can prove this with induction, right, that this will always remain true. Because so long as you're moving the fast one 2 and the slow one 1, since at every point, right, the slow will be halfway through the sorted, or not the sorted, but the checked part of the list. When you get to the end of the list, right, slow will be halfway through the whole list, and fast will be the whole way through the list. So I don't know, I think that's pretty cool. You can kind of use something from another class too, to like prove this is the right way to go about it. But that's the general idea, is that we move the slow 1 for every 2 that we move fast, which kind of intuitively should maybe resonate with you and make you realize, oh, okay, it's going half as far, right? Okay. And then we alternate the value of the control variable to move slow every other iteration. So notice here we have our control variable. And the reason why we're not just doing like each iteration, we're not just moving fast 2 and slow 1, and instead we're only moving fast 1 each iteration and slow every other iteration, is because if we did this, right, if we did fast.next, right, and slow.next every time, then maybe if it's like an odd number of elements, right, or I guess an even number of elements, maybe like 4, then we're going to go out of bounds because we're going to do fast, fast, and then fast, fast. And that's a problem because there's nothing here, right? Or actually, I guess that wouldn't really be a problem because this would be null, right? But if it's an odd number of elements, it is a problem. And I'll show you what I mean. Like we go fast, fast, and then we try and go over 2. And this one is null, so it doesn't exist, but it's null. But null doesn't have a next, so that really is a problem, right? So that's why we do every other iteration of this. Hopefully that makes sense. We move our fast one 2 for every 1 that we move our slow. Right, and that's how we get the middle, because our slow will always be in the middle, because it'll always be the half as far as the fast, because fast moves twice as many, right? So let's look at an example. We have our null head. So null, I'm gonna mark that with like an N for null. We won't enter the while loop, it's just gonna return slow, so that's null, perfect. So if we only have 1 node, so now let's mark this one with a 1, right? Then what are we gonna do? We enter the while loop for 1 iteration, slow doesn't move, return slow, right? Only go 1 iteration because fast is going to be null after that. So again, we just return 1, which is exactly what we want. So perfect so far. But if we have 1, 2, right? That's a little different because we're going to have fast as 1, slow as 1, right? So they're both here. Then we're going to move fast over 1, right? And fast is not null. So I move it over again. Now it's null. But also, we're still in this loop at that point in time, right? At this point, like fast becomes null. So we check if move slow. Well, originally it started as false, but in the very first check, we switched it to true. So now move slow, right, is actually true here. So slow is slow next. So we actually move it over to 2, right? And then move slow is now not move slow. So the next time we wouldn't move it over. But the main thing is that now 2 is our middle. So let's see how this works, right? That's the first iteration, fast becomes 2, slow stays 1. Second iteration, fast becomes null. Because move slow is 2, we actually move the slow one over 1. So that move slow becomes false. But 2 is our middle. Okay, so let's do 1, 2, 3. Again, it's hopefully pretty similar. And hopefully here we're going to get 2, right? Because 2, right, is a middle. So let's check. 1 is our fast, right? So we have fast here. Move slow is false. Then we move over here. And move slow again becomes true, right? After we moved over 1, right? Okay, so let's start again. As of now, fast is here, slow is here, and now move slow is true. So we go through the next iteration. Fast goes over here. And so move slow, as we said, is true. So now slow becomes here, and move slow becomes false. Now move fast over 1. Oh, that's null. And move slow is false at the time. So we swap it to true, but we don't move the S one, right? We don't move slow. So again, we have 2, which is good. That's our middle one. But again, hopefully the intuition of like, okay, basically we're just moving slow 1 for every 2 that move fast. And that's like the crux of this, right? Okay, so first iteration, fast becomes 2, slow stays 1, move slow becomes true. Second iteration, fast becomes 3. So then we also move slow to 2. And third iteration, fast becomes null. Slow is still 2 because move slow became false in the last one. Now move slow becomes true, but fast becomes null, so we don't go any further, and we're done. Right? So questions about that may not be here. So feel free to send them to me on Slack or anywhere. I know it can be a little confusing, but like for real, like if you have questions about this stuff, like ask. I'm more than happy. And I know Joshua is as well. So it's just, yeah. So some exercises here. Late code is pretty good for like practicing technical interview questions as well. So these are pretty good. I recommend doing them if you can. Things like, yeah, valid parentheses. This is a really good, really common stack question, just like in general. So I recommend looking at that for sure if you want to understand stacks better, maybe. Yeah. And these all kind of are linked lists of queues. They're pretty good questions as well. Okay. So again, do the quiz. I have it already. Okay, so that's it for this. There is one more thing I wanted to mention though. So let me actually do that. Okay, this is from another presentation, but I really quickly want to go over it. Okay. So how to write pseudocode, and I'll go over this briefly because I know we are almost out of time. So I'll talk quickly. So write pseudocode. The main thing with pseudocode, I know I didn't go over this last week, but hopefully it helps in future weeks. Pseudocode is getting your point across. Like that's the main thing. Don't worry so much about syntax. It's not a huge deal. Like pseudocode is all about just like get your point across, make it clear what you're trying to say, right? Yeah, like obviously I'm not expecting perfect code out of you guys on like paper or in a Canvas text box. So don't worry about it. Like not a big deal. That stuff in particular. But like it is important that you get your point across in the code. So like for example, like yeah, it doesn't have to be perfect code like this. But for example, like if you wanted to print something, you could just like write print or something like that. Don't make it like all just an essay, because I don't want to see an essay. Like it still needs to like kind of like look and feel like code, but it doesn't have to be exact, right? So this is like pretty similar to just like Java code, but we don't have to write this exactly. Like this is perfect Java code, which is fine. I mean, that's fine pseudocode, but you don't have to do that. You don't have to necessarily use curly braces. Yeah, again, like you can just use print, right? Instead of like cout, for example. So like in Java, for example, it would be something like this, right? It would be for I0, 1100, right? There's no braces here, right? But you have indents to make it clear. And yeah, we use print instead of system.out.println. in Java at least, like in C++, instead of like cout. And notice it's a lot easier to read even for me, right? Or for the reader, it's easier to read. Yeah. So the main thing is that you just want to like make it readable. So even this is kind of okay. Like it can read a little bit like a book. It still needs to look like code, right? Like if you just say loop, if you write out an essay like loop through and like all in one line, for example, like loop through and check if it's divisible by 3 and 5. And then print out the correct stuff. Or like, and then say, like if you just said loop, I can't write, but like loop and check, like loop and check conditions, right? Like if you just said loop and check conditions of divisible by 3 and 5, and then print fizz or buzz depending on what is there, like obviously that's not good enough. But like something like this is good enough because it's pretty close to code. Like it may read a little more like English, but that's fine. Pseudocode is just getting your point across. It doesn't have to compile, and I don't expect it to, but just make it read nicely for you, I guess. Like you don't have to do I mod 3, for example. If I is divisible by 3, right? So it's fine. Yeah, as long as it's clear kind of what you're doing. That's the point of pseudocode. It's not code that will run, but it's code that's going to be clear to a reader and clear to you how it could easily be translated into real code. Just wanted to mention that. Yeah, so try and keep indentation consistent. Use actual keywords where you can, like if, else, or return while, which case you don't, again, like print, fine. Like you don't have to do cout, but yeah. If you pick style, stick with it. Don't do like stack.push the second element and then also push, like don't do all these together, right? Like that's, can you see like how that might be confusing? Because for me to read, because it's like, it means the same thing, but just try and be consistent and make it readable. Again, I'm not expecting like perfect code because like a canvas text box. That's the main thing about pseudocode. And oh yeah, on quizzes in general, my recommendation is always like come up with like some sample test cases in your head and like see if they work. I think that's always really helpful. At least it was for me when I took this class. So yeah. And yeah, just basically pseudocode is just meant to be like readable code. Still, it doesn't have to be like, that's just my advice for like when you take the quiz and stuff, but that's about it. Yeah. Yeah, so this takes a lot of time to write. Like maybe this is a little more clear. So. Okay, so basically just pseudocode, try and write kind of like in the style of code, but it doesn't have to be perfect code. I know that there's a very long-winded way of saying that, but hopefully it's clear and be consistent. And that's about it. Again, if you have any questions about anything, just like send me a message on Slack or email or whatever. And yeah, have a nice rest of your day. Bye, everyone.